Hey everyone! So in this video, I would like to talk about how we find the derivative of a polynomial function. So the first thing that I think is important for us to remember is exactly what a polynomial is. So a polynomial is a bunch of terms that are added or subtracted together. In those terms, we have some variables that are raised to some exponents, a real number, and then we may have some coefficients out front. And then the coefficient in those variables are being multiplied together. So overall, our operations are relatively simple. We have some multiplication, we have some exponents, and then we have addition and subtraction in between our terms. So to find the derivative of a polynomial, as long as we know a couple basic rules, this is pretty straightforward. So let's talk about those rules first. So one of the rules that we need is the simple power rule to help us with the exponents. So remember, this rule says that if I have a function x raised to some power, then the derivative of that function, we bring that exponent down out front, and then we reduce that power by 1. So we get n times x to the n minus 1 power. To take care of our coefficients, we have the constant rule. So I'm going to write this in Leibniz notation. So we have d over dx. This just stands for the derivative. So if I have the derivative of a function that is multiplied by a constant, so here k is going to be my constant, I can actually bring that constant out of the derivative. So this is the same as the constant times the derivative of our function. So this allows me to separate my coefficients from my variables in my polynomial. So now we need to worry about the sum or the difference. So adding or subtracting our terms together. So in this case, let's take a look at the derivative of two functions that are added together. So I'll say f of x plus g of x. So the derivative of this sum is the same as the sum of the derivatives. So this is the same as the derivative of f of x plus the derivative of g of x. And we have a very similar rule for a difference. So the derivative of a difference is the same as the difference of their derivatives. So with a combination of these four rules, we have one that takes care of our exponents, we have one that takes care of the coefficients, and then we have two that take care of our adding or subtracting of the terms. Combining all these together, we can easily find the derivative of a polynomial function. So let's take a look at an example. So here I have a function f of x is equal to 2x to the fifth minus 3x squared. And I want to find f of x. I want to find the derivative of this function. So separating everything out, what I'm going to take a look at is the derivative of each term. And I'm going to write out all of these steps. And I think eventually you don't have to write everything out because we'll get pretty used to this. So firstly, I'm doing the difference of some derivatives. The next thing I want to do is I'm going to take out those coefficients. So this is my constant multiple rule. So I'll bring that 2 out front. So we have 2 times the derivative of x to the fifth. And then we'll subtract 3 times the derivative of x squared. And now just separating it all out like this, now we're doing the derivative of a simple power function. So this is where that rule comes into play. So we have our 2, and then the derivative of x to the fifth, the 5 comes down on front, and then we reduce that power by 1. So 5 minus 1, our exponent is now 4. Then we're subtracting, we still have the 3, and then I'll use my power rule here. 2 comes down out front. We take 1 away from the exponents, we end up with 2 to the first. And then we can finish by simplifying. So then my derivative, f prime of x, is equal to 10x to the fourth minus 6x. So it's a nice, fast process for finding the derivative of a polynomial function. And now that we found that derivative, we can use it to find some other things. For example, let's say we want to find the derivative at 2. So now that we evaluated the derivative, we can just plug in 2. So 10 times 2 to the 4th minus 6 times 2. And simplifying, we get 10 times 16 minus 12. So that is 160 minus 12, which we end up with 148. So f prime of 2 is 148. And I can use that information in a couple different ways. This is telling me that the slope of the tangent line at the x value of 2 is 148, or the instantaneous rate of change at 2 is 148. I could use this derivative function in a couple other ways as well. So let's say we want to write the equation of a tangent line at a specific point. So let's find the tangent line at the point 1, negative 1. So the point 1, negative 1 is on my original graph. So now I want to find the tangent line at that point. So first we need the slope of the tangent line. So to find that, we're just going to find the derivative at that x value of 1. So plugging in 1 to our derivative, 10 times 1 to the 4th power, and then minus 6 times 1. So this is just 10 minus 6, so we end up with f prime of 1 is 4. So that means the slope of our tangent line at this point is 4. So then to write this equation, we can start off with point slope form. So what we have is we have y minus our y value for our point. So in this case, the y value is negative 1, so we'll do y plus 1. And then this is equal to our slope, and then x minus the x value. So there's the equation of the tangent line at that point. And if we wanted to, we could rearrange this. We could rewrite this in slope-intercept form by distributing the 4 and then solving for y. And if we do that, we're going to end up with y is equal to 4x minus 5. So there's our tangent line. But this entire process is sped up partly because we are able to use all these rules to help us quickly find the derivative of our polynomial.